The goal of our project is to model the change of charge on a capacitor with respect to time. The capacitor will be charged using the power generated by a solar panel over the course of a year. To calculate the charge on the capacitor, it will be placed in an RC circuit, a circuit with resistor, capacitor, and a voltage source in series. The simple model is we begin our model by finding a differential equation that represents the change in charge on a capacitor with respect to time. We borrowed an equation from an MIT Department of Physics workshop. We found that solution for this differential equation was Q final times 1 minus e to the negative t over RC. However, this model did not suit our purpose, as it does not account for the fluctuation in voltage of a solar panel. We then modulate the power generated by a solar panel with respect to time.
At its most basic level, the power generated by a solar panel is a function of the intensity of light, I, in watts per meter squared, the area of the solar panel in meters squared, and the angle between the horizon and the sun, phi. This led us to the equation P with respect to t equals I times A times sine of phi. We chose sine because the power function would equal 0 when phi equals 0 degrees, or when the sun is at the horizon, because it is consistent with the real world. We weren't satisfied with just that equation, though. After looking online, we found equations for the position of the sun, as well as the intensity of the sun over the course of a full year. We modified these to fit the needs of our model and added them into the equation. We also found a constant for the efficiency of the solar panels and included that in our equation. Our power equation then looks like this. When the panel is below the horizon, however, no power should be generated. In its current form, P of t is negative when phi is negative. So, to ensure that negative power is not produced during the course of this model, we will limit our function to positive values only by using the max function in MATLAB.
Looking back at our original model, we have yet to define epsilon, the voltage provided by the solar panel. However, we can manipulate the definition of power to produce epsilon in terms of power and resistance. We did this by using the definition of power and Ohm's law. And then substituting this into the differential equation. Now that we have our differential equation, let's take a look at the models. We have created models for our power equation which show power generation over the course of the whole year as well as for smaller time increments. As you can see, power fluctuates over the course of a year, although it doesn't fluctuate as one might imagine. The maximum power over the course of a single year dips at first and then levels off somewhat due to the position of the Earth in its elliptical orbit around the Sun. Over a single day, power increases as the Sun rises and decreases as the Sun sets, leveling off at 0 at night.
Unlike our model for power, our model for charge has a little more intricacy and relies on variables other than just power. The two main variables we tweaked to produce our graph were the resistance and capacitance of the circuit. When the product of the resistance and capacitance, referred to as the time constant in physics, is below 10,000, the graph of charge is very similar to the graph of power. The time constant also affects how the solution looks over the course of a year. When the time constant is roughly between 10,000 and 100,000, the solution changes to be more like the known models for charging and discharging capacitors. When the time constant is greater than about 100,000, the capacitor does not fully discharge during the night cycle, and some charge is preserved from the previous day.
In terms of practical applications of our model, it could allow someone with a solar panel to predict how much charge they will obtain from it, and when that charge be produced. Our model also shows how the capacitor connected to the panel will discharge overnight. If someone is looking to use charge in another way, modeling charge generation can also be useful in determining the area of solar cells required for a specific building. If we had more time to continue this project, there are a few places to expand on it. Variables we could account for in our model include changes in efficiency of the panel over time due to the factors such as degradation of panel materials and dust buildup, changes in resistance due to the temperature, because resistance of a conductor is directly proportional to its operating temperature. Adding a motorized base so that the panel follows the sun more effectively, and we could develop models for different locations on Earth.